In this example, we'll be covering midpoint Riemann sums. In this case, we'll be using 8 subintervals, and it'll be from 0 to 4 on the function x squared one more time. So in this case, I will be drawing once again the same exact function that we just did. I will be going out to 4, but because of the way that this function is supposed to be working, I'm going to have a very difficult time doing what I've done in the past. So now, first of all, let's go ahead and identify the notation for midpoint. Midpoint will be m, and again, since I'm using 8 subintervals, it's going to be m sub 8. I'll go ahead and find my delta x because it, again, is an efficient and consistent way of doing it. It's b minus a divided by n. In this case, it's 1/2. Now, what I'm going to do to efficiently find my midpoints is I'm going to redraw this interval space a little bit larger. I'm going to start at 0. I'm going to end at 4. Okay, now if it helps, you're more than welcome to go ahead and attempt to cut these things in half to the best of your efficiency, like I just did here. Okay, and you'll notice that this is going to go 0 to 1/2. And I'm going to simply add that 1/2 in every single time. So that'll be 1, then 3/2. Technically, I'll go ahead and go straight to 4/2, then 5/2, 6/2, 7/2, and then 8/2. Now again, these, you'll notice, are the exact same interval values on the previous example. What you won't notice is the fact that we're still looking for midpoints, no longer for the endpoints, the left or the right. Again, the left or the right. We're looking for the value in the middle of the two. So what I'm going to go through here is identify a longer axis value arched up. I'm going to call that those are my actual midpoint values. So the easiest way to do this is to first identify what is the distance between these first two values. It's 1/2. And what is 1/2 of that value? 1/4. Okay, so that is actually going to be the midpoint of my first interval. Keep in mind that the small dashes represent my actual intervals. There's 1, 2, 3, 4, 5, 6, 7, as there should be 8. That means that there should be 8 midpoints. 1, 2, 3, 4, 5, 6, 7, 8. Now I found the first one. The way that I'm going to find the second one is one of two ways. I can identify that the distance, the delta x, is 1/4, is the same thing as being 2/4. If I recognize that, then the middle point of this first interval will be this exact same amount of distance, delta x, from that midpoint to get to the next midpoint. So if this is 1/4, my next value should actually be 3/4. And then my next one would be 5/4, 7/4, 9/4, 11/4, 13/4, and finally 15/4. Now just make note here, notice the distance between 0 and 1/4 is 1/4. If I take this 15/4 and add 1/4 to it, I do end up getting to 16/4, which is nothing more than 4. So you'll notice that I have these values right here. These are all of my midpoint values. Those are actually where the intervals are going to be measured towards. So you'll notice I split this up. There's my 1/2, there's my 3/2, there's my 5/2, and my 7/2. And to show this, right here is the point where I'm going to be marking my actual height. That is that 15/4 location. So I'm going to cut it across. I'm going to go ahead and draw this up to that location. I'm going to draw this up to that location. And then I'm going to draw it across. Again, in the middle of this rectangle is the actual location where it's matched. So when I go from 3 to 3/2, that again, I'm looking for the middle of that value, which is about there. And I'm going to go ahead and draw this line up to there and across. So now you'll notice that if you look at these things, there's actually a region above the graph and below the graph that are not counted. And in theory, this should be able to wrap into that spot, or this should be able to slice off and wrap into this spot. Now, we're not absolutely certain that this does this perfectly, but we are certain that this is the best potential estimate for any single graph that a Riemann sum is attempting to approximate. So in this case, let me make sure I have this right. 2, 2, there we go. Yep, right about there. Cut across, right about there. Cut across, right about there. Cut across, and right about here. So you'll notice there, again, if we have 8 subintervals, there are small sections here and small sections here that a little bit are above and a little bit are below. So we can't be perfectly certain whether this is an underestimate or an overestimate. But when I do finally evaluate this 8th midpoint Riemann sum as being the function value at 1/4, that's that right there, times my delta x being 1/2 plus f of 3/4 times 1/2 plus f of 5/4 times 1/2, and so on and so forth. Again, these being just areas of rectangles, and me just adding up those areas. I'm going to go plus all the way up until I get to f of 15/4 times 1/2. Then when I add this all up, I will have 1/2 times 1/4 squared plus 3/4 squared plus 5/4 squared. And again, these are squared because that was the original function we were playing with, x squared. Plus looks like 7/4 squared plus dot 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 until I get to 15/4 squared. Now again, to finalize this answer, all we're going to do is simplify this, type into a calculator, get ourselves a number. And that'll complete that particular problem. I'm not going to actually do that one numerically. What I do want us to realize, however, is how does this graph compare to this graph compare to this graph? Now you'll notice here, if we look at all three of these side by side, our best approximation is definitely this midpoint. And generally that is the case. If I look at my left Riemann sum, in this particular case it is an underestimate. It will not always be the case that a left Riemann sum is an underestimate. If I, for instance, have a different type of function that looks like this, then a left Riemann sum might actually end up being an overestimate depending on the section or the region of the graph that we're playing with. Here, you'll notice is an overestimate for this right Riemann sum. Now, what I do really want you to notice, however, is that this section has a larger space that is outside of the curve, while this one has a smaller generated space that is misstep or uncounted inside the curve. Notice that this changes from 4 to 8 intervals. Now what would you think might happen if, say, I cut these intervals in half and I made it 16, maybe 32, maybe 64? What would you argue is going to happen if I were to cut this thing into more and more rectangles? Arguably, you would say that the area should get closer and closer and closer to being perfectly representative of this curve. So the more rectangles we have, the better estimate it is. Okay, and depending on the method of point that we're going to choose, right, left, or middle, it might change as well.